collection of antennas. Okay, collection of antennas are called an array. Here we are saying that collection of elements. Here each element is a single antenna. Okay. In our last class we have seen. Okay, elements are arranged in one axis. That's why they are called single dimensional array or linear array. Okay, planar array means if you arrange all these elements in a two-dimensional array, they are called planar array. Okay. Here an antenna array is said to be uniform linear array. It is uniform and also linear array. It means that if all the elements are fed with the current of constant magnitude and same phase. Okay, the type of arrays are called uniform linear arrays. Okay. These arrays are broadly classified into two types. Okay, they are broadside array or end-fire array. There is another collinear array also is there. Okay, in our syllabus we don't have. We're not discussing this topic. Okay, collinear array. We'll discuss broadside array and end-fire array cases. Okay, what is an end-fire array? The main difference between the broadside array and end-fire array is that, okay, the radiation, the maximum radiation, based on that maximum radiation, we can decide whether it is a broadside array or end-fire array. Okay, if the radiation is maximum perpendicular to its axis, what is the axis? The line of the array. So suppose we are arranged a group of elements or array is a collection of antennas. We are arranging the antennas in such a way that, okay, they are a linear array. They are in a straight line. Okay, if the radiation is maximum perpendicular to its axis, then it is called broadside array. Okay, if the radiation is along the axis or parallel to that axis is called end-fire array. Okay, if the elements are arranged in coaxially means in different angles. We have 360 degrees, right? You can place different types of angles, then they are called collinear array. This collinear array of antennas also you can see in weather prediction centers. Okay, they are measuring different atmospheric pressure, atmospheric parameters. Okay, this broadside array and end-fire array, they are used in communication purpose. First, we'll see the broadside array case. Okay, here first we'll start with the 2 point sources or two elements. Okay, or 2 antennas. Then we will extend it to the n number of antenna elements. Okay. Here, let us consider we are assuming we are having 2 isotropic antennas. Okay, they are placed in a different. They are placed. That's the separation, the distance between the 2 antennas is, let us assume it is a d. Okay, this d may be lambda by 2, lambda 2 lambda, different distance separation we can assume. Okay, later we'll see what are the different types of patterns we are having. Okay, here we are assuming 2 isotropic point sources. Okay, assuming the 2 point sources with the same equal current and magnitude, equal magnitude and phase. Okay, we are giving as an input to these antennas. Okay, here let us assume we are having an observation point P. The distance between the reference point and the source A1 and A2 is R2. Let us assume here this is the, here at A1 we are having one isotropic antenna. At A2 we are having another isotropic antenna. Okay, we have to find out the resultant electric field or magnetic field at the observation point P. Okay, we already know that. Okay, the electromagnetic waves generated by this antenna, they have to travel more distance compared to the electromagnetic wave front generated by this isotropic antenna. Okay, isotropic antenna at A2. Okay, here the distance, let us say this is R2, this is R1. R1 is always greater than R2. Here the extra distance these electromagnetic waves are traveling, this is called the path difference. Okay, the path difference is d cos phi. Okay, we are how to find out how to get the d cos phi. This is the distance. We know the angle. This is the pi, and this is the d. Okay, here is the rectangle. Okay, this is the diagonal. Therefore, the distance. This is the length. This is d cos phi. This is d cos phi. Okay, from we know that this is the okay. This is the path difference. From the path difference, we can able to calculate the yes. Still students are joining. Okay. Okay, the path difference is given by d cos phi. Okay, the path difference in terms of the wavelength, we already seen these things. Okay, with respect to the wavelength, the path difference is d cos phi divided by lambda. Evara 499, what are you doing? Sunil. Okay, here this is the path difference with respect to the in terms of wavelength is d cos phi divided by lambda. We already know that the phase angle is denoted by psi. Phase angle is equal to 2 pi times of the path difference. Okay, if you substitute here path difference d cos phi by lambda, okay, 2 pi by lambda is equal to beta. Beta is the phase shift constant, we know that. Okay, therefore the phase angle is equal to bd cos phi. Okay, here we are assuming at the at antenna A1 and A2 there is a two isotropic antennas. Okay, let us assume the electric field due to the isotropic antenna A1, that is E1, and E2 is the electric field intensity due to this antenna, isotropic antenna at A2. Therefore, the resultant electric field, E is equal to the the resultant electric field at the observation point P is equal to ET is equal to E1 plus E2. Okay, we know that how to represent E1 and E2. Okay, with the same same current with the same magnitude and phase. Okay, because of the separation between these two sources. Okay, this is the normal we will represent. E1 is equal to E naught e power minus j psi by 2, and similarly we can represent at the current source due to the isotropic source at A2. The electric field is represented as E2 is equal to E naught e power j psi by 2. Okay, because of the path difference, here we are using this is minus psi by 2 and this is plus psi by 2. Okay, from here the derivation is very simple. The resultant electric field is equal to E1 plus E2. Substitute in this equation E1 and E2. We are getting this is e power j psi by 2 plus e power minus j psi by 2. That is equal to e power j theta plus e power minus j theta is equal to 2 cos theta. Therefore, what is psi? I am substituting here psi is equal to bd cos phi. This is by 2, right? That way we are writing by 2 here. This is the resultant of the resultant electric field due to the electric field produced by the antenna A1 and A2. Okay. This is the equation. You have to remember that. Okay, for the 2 point sources, we are giving the same input. Okay, the current is having the same magnitude and phase. If you change the phase, okay, different patterns will come. First of all, for our understanding purpose, we are assuming we are giving the input to this antenna having the same magnitude and phase. Okay, same magnitude and phase. Okay, now we have to find out, this is the electric field, right? We can, from this you can plot the radiation pattern. Okay, first of all we want to find out the direction of maxima. Okay, in which direction the electric field intensity is maximum. How to find out that electric field intensity maximum means? Okay, from the equation 1, let us say this is our equation 1, when the electric field intensity will be maximum. Okay, the cos bd cos pi divided by 2, if it is maximum, then the electric field, the resultant electric field intensity is maximum. Okay, therefore cos bd cos pi divided by 2 is maximum. Okay, when it is maximum, what is the maximum value here? The variation of cos bd cos pi by 2 is in the range of plus or minus 1. Here you have to assume the different distances. Okay, here we'll assume the మళ్ళీ రూపాయి ఎవరు మీ క్లాస్మేట్ అనా? అమ్మాయి రోల్ నెంబర్తో జాయిన్ అవ్వమని చెప్పి జాయిన్ అవుతాయి. Somebody is joining our class. Her name is Malli Rupa. It is a scam or virus, you can leave it. Okay, let us assume the distance between the two antennas is d is equal to lambda by 2. Okay, if the distance between the two antennas is lambda by 2, now substitute in this above equation, we are getting based on this distance, we are getting the maximum. Okay, main lobe and side lobes in different directions. Okay, we'll get a beautiful pattern. First of all, we assume d is equal to lambda by 2. Substitute here. Okay, so if substitute here, this is equal to d is equal to lambda by 2, you are getting cos 2 pi by lambda, lambda by 2, cos theta by 2. This is equal to plus or minus 1. Now this is equal to cos pi by 2, cos pi. This is equal to plus or minus 1. Therefore, pi by 2 cos phi. Okay, this is equal to cos inverse of plus or minus 1. This is equal to when the cos will become plus or minus 1, that is based on plus or minus n pi. Okay, what is n? N is equal to 0, 1, 2, 3. Suppose n is equal to 0. If n is equal to 0, this is equal to pi by 2 cos phi maximum. This is equal to cos inverse of 0. When the cos 0 0, therefore we are getting 0 here. Okay, this is one condition. If you take different values of n, we are getting different values. Okay, suppose if n is equal to 1, then n is equal to 1 means what is that? When this is, whenever getting the 1, cos 0 is equal to 1. Okay, what is this? Plus okay, n is equal to 0 means this is 0. Okay, when n is equal to 0, now cos pi is equal to, now see here, very simple, this is plus or minus n pi. N is equal to 0 means pi by 2 cos pi maximum is equal to 0. Therefore this pi by 2 and this is 0, right? That's why if you multiply anything, that also will become 0. Therefore the cos pi maximum is equal to 0. When the cos pi is equal to 0, the different values of cos 90 and 270 and so on. Okay, therefore the maximum radiation, the maximum electric field intensity is in the direction of 90 degrees and 270 degrees. Okay, from 1 second, this is not stuck for me. Okay, the direction of maxima based on this electric field, based on the electric field intensity equation, okay, we can see that it is maximum in 90 degrees and 270 degrees. Similarly, what is the direction of minima? Okay, direction of minima means the electric field intensity is 0. Okay, when it will become 0? Okay, the cos BD cos pi by 2 is equal to 0. Okay, if it is 0, okay, you can say what is the cos inverse of 0? Okay, we already substituted d value. D is equal to lambda by 2. Beta is equal to 2 pi by lambda. Now we are getting cos pi by 2. Cos pi is equal to 0. Okay. Therefore, if you apply inverse on both sides of this equation, pi by 2 cos theta is equal to cos inverse of 0. Okay, cos inverse of 0. Okay, what is the value of cos inverse of 0? When the cos will become 0? Pi by 2. Okay, multiples of pi by 2, right? Suppose n is equal to 0, this is pi by 2. If n is equal to 1, 3 pi by 2. Okay, like 5 pi by 2. For all these values of values, okay, the cos is 0. Therefore, okay, when pi by 2 cos phi is equal to plus or minus pi by 2, 2n plus 1. Okay, plus 2n plus 1. For all these values, the cos is 0. Therefore, cos pi is equal to, okay, this pi by 2 and this pi by 2 will get cancelled. Cos pi is equal to plus or minus 2n plus 1. Okay. Therefore, okay, when this suppose n is equal to 0, substitute n is equal to 0. Okay, this cos pi minimum is equal to plus or minus 1. When it will become plus or minus 1? Plus 1. Cos 0 is equal to plus 1. When you are getting minus 1, cos of 180 degrees. Cos 180 is equal to minus 1. That's why the electric field intensity for placing these two isotropic antennas in a the distance between the distance of separation between the two antennas is lambda by 2. We are getting the minimum. Okay, the minimum radiation intensity in the direction of 0 degrees and 180 degrees. Okay, if you plot, if you see that plot also, you can see, okay, see like this. Okay, minimum in the direction of, see, this is the maximum. The electric field intensity is maximum in the direction of theta is equal to 90 degrees and, sorry, phi is equal to 90 degrees and phi is equal to 270 degrees. It is minimum or 0 in the direction pi is equal to 0 and 180 degrees. We also find out the half power points also we can able to calculate. Okay, see here, this is the direction of maxima, this is the direction of minima, and this is direction of half power points. Half power means here this is the electric field strength. That's why, okay, the value of this is 1 by root 2. Power means E square, right? That's why half power. How will get the half power? This is if you want to square the electric field intensity. Okay, that's why we are writing 1 by root 2. Okay, half power. We want half power. Okay, this is the electric field strength. E naught is ET is the electric field strength. That's why we are taking 1 by root 2. If you square this, okay, if you square this, we are getting 1 by 2. That's why we'll get in the half power. Okay, for half power points, how to calculate the half power point, the angle. Okay, for that, okay, this value is equal to plus or minus 1 by root 2. When this will become plus or minus 1 by root 2, this is equal to cos pi by 4. Cos pi by 4 is equal to 1 by root 2. Okay, different values are, suppose cos pi by 4. Okay, suppose n is equal to 1, 2 pi by 4 means pi by 2. This is wrong. Okay, only for um, cos pi by 4 only, cos 45 degrees. Okay, 45 degrees only we are getting uh, Okay, this is plus or minus 1 by root 2. Okay, for that reason, okay, now take n is equal to 0. Okay, we are getting pi by 4. Cos pi by 4 is equal to 1 by root 2. Okay, plus or minus, right? Okay, if you add, what is the value of, okay, don't worry about that. Let us take, this is plus or minus pi by 4. Okay, for n is equal to 0, we are getting cos pi by 2 cos pi is equal to pi by 4. We'll get pi by 4. Okay, this pi and this pi will get cancelled. We're getting 1 by 2. Cos pi is equal to plus or minus 1 by 2. Okay. Okay, for okay, this thing, okay, you can at present, okay, take this as a pi by 4. We'll see later what will happen. Okay, this is cos inverse of less or minus 1 by root 2. This is nothing but plus or minus pi by 4. Cos pi by 4 is equal to 1 by root 2. Okay, now, okay, now this is cos pi is equal to, we're getting this pi and this pi will get cancelled. This is half. When this cos pi is half, plus or minus half, that is for 60 degrees and 120 degrees. Okay, this is clear, right? Dear students, for half power points you are getting the angle pi is equal to 60 degrees and 120 degrees. Okay, therefore, if you plot the radiation pattern of the resultant electric field intensity of the two isotropic antennas placing lambda by 2 distance, okay, the radiation pattern is like this. The maximum in this direction of pi is equal to 90, minimum in theta is pi is equal to 0 and 180 degrees. Okay, similarly you can plot for different directions, okay, different distance between these 2 points. If it is lambda, okay, if it is lambda by 2, we're getting like this. If it is lambda and 2 lambda, there are different patterns are there. Okay, I will show you after some time, okay, how the this radiation pattern will look like if the distance between these 2 antennas is lambda and 2 lambda also, we will see. Okay, before that, okay, here I am considering this end-fire array case. In end-fire array case, we are taking the 2 isotropic antennas. Okay, the difference between the two isotropic antennas is lambda by 2, but we are giving the different phase to these antennas. Okay, same problem. Okay, same problem, but we are giving the here we are giving the input to these 2 antennas with the same magnitude but different phase. Okay, the same, everything is same here. Okay, here E2 is equal to, see here, here the resultant of the electric field at the observation point P is equal to minus of E1 plus E2. Why this minus of E2? There is a phase difference between 90 degrees phase shift difference between these 2 currents that are given to the antennas. That's why we can write here E1 is equal to E0 e power minus j psi by 2, E2 is equal to E0 into e power j psi by 2. But the total electric field, because of they are opposite in phase. Okay, we are giving the currents to the elements. Okay, the magnitude is same, but the phase is opposite in phase. Opposite in phase means 180 degrees. 180 degrees means we are getting minus sign. Okay, okay, if you now this is the equation, the resultant equal minus E1 plus E2. Okay, if you substitute here, we are getting earlier e power j theta plus e power minus j theta. Now e power j theta minus e power minus j theta, that is nothing but 2j times of E0 sin BD cos phi divided by 2. Okay, because of this 180 degrees phase shift, earlier we are getting cos, now we are getting sin. For this also we can calculate the direction in the maximum. When it is maximum, this value will becomes maximum, then we are getting the maximum radiation intensity, electric field intensity in that direction. Okay, for that reason, maximum means the sign value is maximum plus or minus 1. Okay, plus 1 you can take. Here d is equal to lambda by 2. Okay, if you substitute here, okay, when the sign this is equal plus or minus 1, this is sine pi by 2 cos pi is equal to plus or minus 1. When the sign will become 1, that is equal to pi by 2, okay, 3 pi by 2 and 5 pi by 2. Therefore, if you take, suppose this is equal to pi by 2 cos pi is equal to 2n plus 1 to pi by 2, pi by 2, pi by 2 get cancelled. Cos pi is equal to plus or minus 2n plus 1. If you take n is equal to 1, cos pi is equal to 1. When cos will become 1, 1 and plus or minus 1, cos 0 is equal to 1 and cos 180 also, cos 180 equal to minus 1. Therefore, okay, therefore in this case, two isotropic antennas with same magnitude and 180 degrees phase shift, we are getting the maximum in 0 and 180 degrees. 0 and 180 degrees. Okay. Similarly, minimum, if you take the minima, this is equal to 0. Okay. If you say cos pi is equal to 0, when this is equal to 0, 90 degrees and 270 degrees, cos equal to 0. That's why we are getting the pattern like this. See, because of changing the phase difference, giving the same input, by changing the changing the phase of the signal that is given to the antennas, we can able to getting different radiation patterns. See how beautifully here the radiation is maximum. This is the axis. Suppose we combine these two antenna elements. This is the axis. Along the radiation is maximum along this axis. That's why it is called end fire array. Earlier we are giving the same phase. Okay, for that case we are getting the, this is the two antennas. This is one and two antennas. This is the axis of the array. Now the radiation is maximum perpendicular to this axis. That's why this is called the broadside array. See how beautifully, if you change the phase that is giving to the antenna, we can able to change the radiation pattern of the antenna. Dear students, we have only 2 minutes left. Okay, I will stop here. From tomorrow class I will continue. Today we have seen the two antenna arrays case. Tomorrow we'll see n elements. We'll take n elements and we'll try to find out we'll get the same kind of pattern. You can see. Okay, I will share. I forgotten to share the slides in the last class slides. Okay, today after completion of my class, I will share the slides. Okay, somebody in the class, please help me to take the attendance. Somebody in the class, please help me. Who will going to help me? Swarup, are you there? Swarup unnara? Inka unnaru? Shilpa gani, Pujita gani, inkevaru mee class lo CR LR పేర్లు మర్చిపోతుంటానే.
sir.
Please ma, help me. Fast.
83,
83,
84, 86, 87,
84, 86, 87,
88, 91, 92,
88, 91 amma.
91, 92, 89 absent, sir.
90 కూడా absent amma.
Absent, sir.
Okay amma, okay. Next fast episode.
93, 94, 96, 93, 94, 96,
94, 96,
97, 98, 99,
97, 98, 99,
A0, A1, A2, A3,
A0, A1, A2, A3,
A6, A7, A8,
A6, A7, A8,
B0, B1, B2,
B0, B1, B2,
B4, B5, B6,
B4, B5, B6,
B7, B8, B9,
B7,